Good morning, students. Welcome to the session to learn about Wheatstone bridge sensitivity. So, in the last class, you learned about to find out the unknown resistance R4. That is nothing but the ratio of R1 and R2. That is R1 by R2 into R3 gives you R4, where the R1 and R2 are called the ratio arms, and the R3 is called as the standard arm. When the bridge is not balanced, the current flows through the galvanometer, causing the deflection in the galvanometer. That is, it will show some reading so that it indicates that current flows through the galvanometer, and there exists a potential difference between the points B and D. Whenever there is a potential difference between the points B and D, there will be a current flowing through this that branch where the galvanometer is connected. Here you are going to learn about the sensitivity, or you are going to derive for the sensitivity of the bridge. Before we start with, we'll see what is the importance of the sensitivity, or what do you mean by sensitivity. Sensitivity in general term can be defined as, or its ability to distinguish between two close value. In terms of the circuit or the bridges here, or the Wheatstone bridge or the Kelvin's bridge, whatever it is, the sensitivity can be explained like whenever there is a change in the input, you are measuring the resistance R4. Suppose the R4 value is changed, accordingly whether that is deflected, or accordingly whether there is the change in the output. Whenever there is a change in the input, accordingly the circuit is responded, or accordingly there is a change in the output, is nothing but you can say sensitivity. Here, so whatever you are measuring the value of the resistance, then the value of the resistance is changed, that should be reflected in the output, is nothing but sensitivity here. So you can say the sensitivity is closely associated with the accuracy also. So the amount of deflection depends on the sensitivity of the galvanometer. The amount of deflection, how much the needle is getting deflected, that depends on the sensitivity of the galvanometer. If the galvanometer sensitivity is very poor, for some smaller changes it is not able to respond, or that same cannot be reflected in the output. If it is more sensitive, if the galvanometer is more sensitive, you can say even for a small change that can be detected, or that can be responded, or that can be shown in the outputs. Now you can understand very well what is the meaning of sensitivity. The amount of deflection depends on the sensitivity of the galvanometer. The sensitivity can also be expressed as the amount of deflection per unit current, or the amount of deflection per unit voltage. When it is expressed as the deflection per unit current, it is current sensitivity. So the sensitivity can be written as S is equal to deflection by current. S is equal to D by I, where D is the deflection, I is the current. So sensitivity S is nothing but deflection by current per unit current. Per unit current, how much it is deflected is nothing but sensitivity. It also can be expressed as millimeter by microamps, mm by microamps, or the radians per microamps, or degrees per microamps. So another way of representing the galvanometer sensitivity is the amount of deflection per unit voltage across the galvanometer. The amount of deflection per unit voltage, when it is written as or expressed as the amount of deflection per unit current, it is called as a current sensitivity of the galvanometer, or it can be also expressed as in terms of or the amount of deflection per unit voltage is nothing but the voltage sensitivity of the galvanometer, and it is mathematically expressed as S is equal to theta by E. V stands for voltage sensitivity. So voltage sensitivity is nothing but deflection per unit voltage. Deflection is expressed in terms of theta and the voltage is expressed in terms of E. So where V is the voltage across the galvanometer and theta is the deflection of the galvanometer. It is measured in degrees per volts or the radians per volt. For the current sensitivity, it is measured in terms of degrees per microampere and also or radians per microampere. Since it is for the voltage sensitivity, deflection per unit current for unit voltage, it is expressed or measured in terms of degrees per volts or the radians per volts. So the Brix sensitivity is defined as the deflection of the galvanometer per unit fractional change in the unknown resistance. It is denoted as SB. The current sensitivity is nothing but the deflection per unit current, and also we have seen the voltage sensitivity is nothing but deflection per unit voltage. Here another term called Brix sensitivity. It is defined as the deflection of the galvanometer per unit fractional change in the unknown resistance. It is denoted as SB. So SB can be written as the amount of deflection, that is theta. The change, the unit fractional change is written as del R by R, where del R by R is the unit fractional change in the unknown resistance. It is nothing but the Brix sensitivity. So we'll go for derive an expression for the sensitivity. You just consider the bridge under small unbalance. The bridge is not balanced. What is the outcome of this? When the bridge is not balanced, we can say the potential difference between the points B and D is not same. So there is exits difference between B and D. So there is a current through the galvanometer, or you can say a small deflection will be there in the galvanometer. So at balance condition, we have come across the expression called R4 is equal to R1 into R2 into R1 by R2 into R3, or you can write R4 by R3 is equal to R1 by R2. It is for balance condition. Now the circuit is not balanced, it is under small unbalance. Let the R4 is changed by del R, creating the balance. How this unbalance is created? So already when it is balanced, R4, the ratio of R4 to R3 is equal to the ratio of R1 to R2. When there is a change in R4, you can say the circuit goes to unbalance. So the unbalance is introduced by changing the value of R4. So let the resistance R4 is changed by del R, creating the unbalance. Due to this, the EMF appears across the galvanometer. So that EMF should be calculated. So to calculate the EMF across the galvanometer using the Thevenin's theorem, we are going to find out the Thevenin's voltage and also the Thevenin's resistance to find out, due to that small deflection, what is the current through the galvanometer. So what is the Thevenin's theorem? A circuit with single source or the many source with many branches or the many loops can be expressed as one voltage source in series with the resistance along with the load. So that is nothing but the Thevenin's equivalent. So when a circuit is converted into a Thevenin's equivalent, it is easy to analyze the circuit, or it is easy to find out the current through the load. So using the Thevenin theorem, we are going to find out the current through the galvanometer. So using the theorem, we need to calculate Thevenin's voltage, that is VTH, and also the RTH, that is R equivalent. We need to find out. First we will start with VTH. So if you consider the loop ABDA, there are R1 you have, then B2D, VTH. So to find out the open circuit voltage, Thevenin's voltage is nothing but the open circuit voltage. So we need to calculate the current through the galvanometer. So that galvanometer is removed, that circuit is open now, that branch is open now. The voltage across that branch, that open circuit voltage, is nothing but, or it can be represented as VTH. So when you consider ABDA, using the mesh equation or the loop equation, you can add all the voltages and you can find out what is VTH. So you can write the voltage across AB plus V Thevenin minus EAD is equal to 0. You just move along the path in the clockwise direction, that is from A to B, B to D, then D to A. From A to B, the voltage across R1 is nothing but, or you can write the voltage across AB, EAB. Similarly, the voltage across B to D, it is VTH, or then the voltage across D to A, or it is EAD. You can see the direction of the current I1 from A to B, the direction of A to D, here the another current I2. So when you write the loop equation, VAB plus VTH, when you see the current through AD, it is in the opposite direction. So minus EAD is equal to 0. From this, VTH can be written as EAD minus EAB. What is EAD? EAD is nothing but, the resistance across EAD is nothing but R4 plus del R. The current through that is nothing but I2. So you can write EAB is nothing but, across A and B you have R1 and the current through R1 is I1. So I1 R1 is nothing but EAB. Similarly, you can write EAD also. From EAB, I1 and R1 already we have seen, I1 is nothing but E by R1 plus R2. When that is substituted here, EAB can be written as E into R1 divided by R1 plus R2. Similarly, EAD can be calculated. EAD is nothing but I2 into R4 plus del R, but I2 is nothing but E by R3 plus R4 plus del R. So that is substituted in the equation. EAD is equal to I2 into R4 plus del R, so that we will get it as EAD is equal to E by R3 plus R4 into del R into R4 plus del R. So we have calculated EAB and EAD. V Thevenin is nothing but EAD minus EAB. So when that is performed, that is V Thevenin is equal to VAB minus VAD. So VAB value and VAD value substituted here. Since E is common here, when that is taken out, again with the condition when R4 by R3 is equal to R1 by R2, then you can write R1 divided by R1 plus R2 is equal to R4 divided by R3 plus R4. So wherever you have R1, that can be replaced with R4. Wherever you have R3, that can be replaced with R2. because R4 by R3 is equal to R1 by R2. So R1 by R1 plus R2 can be written as R4 divided by R3 plus R4. So that Thevenin can be written as E into R4 plus del R divided by R3 plus R4 plus del R. Here R1 by R1 plus R2 is substituted as R4 divided by R3 plus R4. So when that is substituted, and you do cross multiply, you will get it as, so R4 plus del R, when that is expanded, you can see many terms get cancelled. So finally you can write VTH is equal to E del R by R3 divided by R3 plus R4 the whole square divided by E plus del R into R3 plus R4. So when del R, the change in R4 is very small compared with R3 plus R4 the whole square, then that del R into R3 plus R4 can be eliminated. So you can write E is equal to del R, E del R into R3 divided by R3 plus R4 the whole square. So that's all about this VETH. We'll see in the next class how the R equivalent is calculated, and accordingly what is the sensitivity of the bridge.